Hello everyone, welcome back to another Geostats lecture video. And in this lecture video, I want to begin our discussion talking about spatial regression. Right, and so if you remember back to our previous discussion, right, when we were discussing regression, right, we said we had ordinary least squares. Right, ordinary least squares regression, which we said had an equation that looked something like this, right? We had our y hat, which was our estimated value, equaling this term we called beta naught, which was the intercept plus, and then we had a series of things that look like beta x1 times x1 plus beta x2 times x2 dot 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 dot. And then we have this thing here called the error term. Right, so this was our general equation for ordinary least squares. And we said that the point of this equation was to come up with a relationship between all of these x's, which we call their independent variables, and our our dependent variable, which was our y. And that this beta naught was what would happen if our x's didn't exist, right? If all of our x's were 0. And so we came up with some pretty good regression formulas, right? This seems like it works pretty well. But if we put this in the context of geography, right, we also know about this thing called spatial autocorrelation, right? Right, we've talked about spatial autocorrelation in the past, right? And that, to sort of recap, right, that's the idea that you have geography playing a role, and that the things that are closer together are going to have more similar values than things that are farther apart. And basically what we're saying, to sum up spatial autocorrelation, is that location matters, right? That's the whole idea. Well, these two things right now are so the idea with spatial regression is to figure out a way to take this spatial autocorrelation that we discussed before and bring it into this idea of least squares regression, right? And so I'm not going to spend a whole lot of time in this module talking about either of these concepts because hopefully we have a good understanding of them. What I do want to do in this module and in the next module is talk about some ways that we can incorporate this into here. And for this module specifically, I want to talk about the idea of spatial lag. And we're going to spend the next couple of videos going into more detail what spatial lag models are and how to interpret them. But what I want to do right here is I want to just throw out this idea of spatial lag X models and the spatial lag Y model. And sort of outline conceptually what they mean. So the spatial lag X model is basically a way of saying, hey, we have all of these non-spatial things, right? The values of the data set that we are saying have some relationship to our dependent variable. Well, what if we also were going to say that it's not just my x value, right? Because these x's are for an individual record, right? An individual polygon or an individual observation, right? To predict that observation's y. For the spatial lag X model, what we're saying is, what if my neighbor's x's right, impact my y? Right? What if what's going on in my neighbors in terms of the way that their variables, right, their independent variables are doing, what if those affect me, right? That's the concept of spatial. And we've already kind of seen this with the idea of the lagged means, right? Where we calculated the average of the average value of your neighboring polygons, right? That was your lagged mean. Well, if you'll notice, lag here, we're doing that in much the same way. And as we'll talk about in the next video where we go through the equation for these models, you'll see that we're actually pulling in that exact same concept of spatially lagged means to account for this idea of what if my neighbors affect me. So that's the lag x. The lag y asks a similar question, but it's saying, what if my neighbor's y impacts my y? All right, so now with the spatial lag model, it's not so much talking about the independent variables as it is saying sort of, I don't want to say directly because that's a little confusing, but it's saying what if the thing I'm trying to predict is impacted by that same thing that's occurring in my neighbors. So if we were to talk about smoking, for example, right, you might have all of these variables that might predict smoking. But what if, in addition to all of those things, simply knowing something about the smoking rate of the neighboring polygon would also impact, right? If there's a high smoke rate in the neighboring polygon, is that going to give an indication of what's happening in my polygon? So spatially lagged x models the x's, spatially lagged y models the y. And so one last point that I want to make here with spatial regression is that spatial regression, let me give myself a little more space here. And I'm going to make this a different color because I kind of want this to stand out. Is that spatial regression, spatial regression is not about making predictions. Right, and this kind of makes sense. If you think about back to the idea of the lagged means, right, where the connectivity mattered, right, how the polygons were arranged to each other mattered. So these spatial regressions are kind of dependent on that network. And so it doesn't make a whole lot of sense necessarily to take the network and apply it to a different data set. You certainly can do it, right? It is possible to make predictions. But spatial regression is not about making predictions. It's about finding patterns. It's more about finding patterns. And looking for how things affect each other. So hopefully that makes sense. And again, we're going to be going through the equations and interpretation of all of these things in future videos. So if you have any questions, please reach out. Thank you.